Good morning, everyone. This is Dr. Shahabuddin Ahmed. In this presentation, I will be talking about decarbonizing heavy industries using hydrogen energy, and followed by a case study for steel manufacturing. Currently, I'm working at Swinburne University of Technology, and previously I worked at Federation University of Australia and UNSW Sydney as a postdoctoral research fellow. I did my PhD from Monash University. The purpose of this study is to boost process efficiency and mitigate CO2 emission in order to achieve net zero emission target by 2050. In order to achieve this goal, we have three main objectives. Firstly, to identify the challenges to the integration of hydrogen in heavy industries. While I talk about heavy industry, that means transport sector, different manufacturing industries. For example, steel is one of them, agriculture and power sector. Secondly, techno-economic analysis of hydrogen generation technologies as well as its implementation in different processes. And finally, life cycle analysis for hydrogen generation technologies as well as the process where we implement hydrogen energy. So this is a key figure in steel industries. Worldwide, 1.8 billion ton of steel is produced per year using ore, DRI, and scrap. And in order to produce those steels, we need to use 800 kilograms of coal per ton of steel manufacturing, especially using traditional blast furnace method. So we have mainly two methods. One is blast furnace, basic oxygen furnace, which produces about 70% of steel in the world. And secondly, electric arc furnace, which produces 25% of steel in the world. And the rest of the processes produces 5% steel. Steel industry is very energy intensive process. About 8% of world energy is consumed by steel industries, and 7 to 9% emission is coming from steel industries. That means we need to heavily focus on this area in order to meet net zero emission target by 2050, which most of the countries have agreed on in the United Nations conference. So this is the traditional steel manufacturing process. Firstly, the blast furnace process, and secondly, smelting reduction. Thirdly, direct reduction, and finally the scrap recycling, which is in electric arc furnace. First two uses a basic oxygen furnace, and the other tools use electric arc furnace to produce steel. So in order to mitigate CO2 emission from steel industries, because steel industries produces about 2 ton of CO2 per ton of steel manufacturing, particularly using those blast furnace techniques, and subsequently smelting reduction and direct reduction process as well. But those two process produces less emission as compared to blast furnace, and the steel scrap recycling, of course, produces comparatively lower CO2 because those processes of coal and the fine ore or the pelletization are not involved in the steel recycling, steel scrap recycling process. So there has been some studies or some development in order to reduce the CO2 emission from blast furnace techniques. Some innovative process have been developed over the years using different techniques. For example, Finex, Finmet, Hismelt, and Hisarna. So those techniques is also basically based on coal or fine ore. Some processes uses natural gas as well. So, but unfortunately, those processes could not reduce CO2 emission over 20 to 25%. Some processes are still under development. For example, coke oven gas in Kuros 50 project, which can potentially reduce CO2 emission over about 30%, but that will take until 2030. And some other processes include biomass and plastic, which can also reduce 20 30 to 50% of CO2. And recently, some companies in the world are introducing hydrogen in their process, blast furnace process, to reduce CO2 emission. But potentially, as much as we can get the data, about 30% CO2 can be reduced. ThyssenKrupp is one of them. Some other companies include Midrex and HYL, but they are introducing different techniques. So these are some emerging technologies. For example, hydrogen-based DRI and integration with electric arc furnace, hydrogen plasma smelting, as we can see in the figure. These are the techniques. Alkaline iron electrolysis, molten oxide electrolysis. So these are the potential technique, but this is very much in early stage of the development. So this is their development so far. We have using different technologies, and I mentioned over based on technology readiness level. As you can see, blast used, so it's already developed. Other technologies which are still under development include use of biomass, as I mentioned, Hisarna, and so these are the traditional method, but with some modifications. But these are the emerging technologies which are hydrogen-based DRI. Among those other three, like hydrogen plasma, alkaline, and molten oxide, among those four technologies, hydrogen-based DRI is the most advanced one, and we expect it to be industrial development by 2035. Other technologies, if all goes well, all other technologies will be potentially come in industrial development by 2050 or even earlier. So this is a case study with a company, steel manufacturing company. We calculated how much hydrogen they need in order to replace their existing process. As you can see, this line shows. This orange line shows the natural gas they need to they will be reducing and substituting with hydrogen, which is the blue line. And secondly, the consumption of hydrogen with respect to the volume of hydrogen and natural gas. And the third one is the cost associated with the hydrogen as well as with compared to natural gas. And followed by that, we did process modeling using two most common method, which is alkaline electrolysis as well as steam methane reforming. So as we can see in the left hand side, I calculated based on the energy need for that company, and showed that if they need to use electrolyzer, how much energy how much would be the energy consumption and what would be their output of hydrogen, and what would be the output of chemical energy from hydrogen. And in the bottom figure, we can see that what is the temperature, optimum temperature we need to use in order to do steam methane reforming. This is catalytic based, but this data can vary depending on the operating condition or the catalysis you use. And finally, life cycle analysis. So the left hand side is the cost of the electrolysis using a proton exchange membranes technology. So we can see so currently the cost is a bit high, which is over $6, and over the years it will be decreasing. But this data also again depends on the assumptions and your scenario analysis. And in the right hand side, you can see the impact from different technologies. Like I calculated 6-7 technologies life cycle impact or the impact on the environment in considering human health, ecosystem, and the different resources. You can see the impact using different technologies. So these technologies, like for example, this is the highest impact from proton exchange membranes because this used grid electricity. At this moment, we don't have enough electricity from renewable sources. Of course, this impact will be significantly decreased or even lowest while we use renewable electricity. In conclusion, I would say hydrogen is a promising energy and fuel sources, which has very much potentiality to reduce CO2 emission from heavy industries. Because the use of hydrogen is very versatile. You can use it as a fuel or, as well as an energy carrier. So the main barrier is availability of cost-effective renewable hydrogen, which we need to focus on how we can generate hydrogen as quick as possible with lowest energy, which is compatible, which is convenient and competitive with the existing process. And thorough investigation for the process performance is also required because there are so much technical issues using hydrogen integrated process, which we need to study either in studying from the lab scale to the pilot scale and the commercial scale. So, and that will lead to the modification of existing process for hydrogen integration. And finally, developing operating procedures and a safety protocol based on the scenario and the processes. For your attention, if you have any questions, feel free to send an email to me at sahmed@sweden